It's mysterious and wondrous. Welcome to the world of relativity. This video does not involve relativity, but introduces Lagrangian mechanics. As in subsequent videos, we will explore relativistic dynamics within the framework of Lagrangian mechanics. Mechanics, simply put, is a mathematical model used to describe and predict the motion of objects. In the field of classical mechanics, major models include Newtonian mechanics, Lagrangian mechanics, and Hamiltonian mechanics. Each model in classical physics represents a different mathematical framework. Although they describe the same physical reality, the mathematical infrastructures of each model are distinct. Newtonian mechanics is the earliest model of mechanics. In this model, the core concept is F equals m times a, attributing changes in velocity or acceleration to the action of forces. The integral of acceleration over time gives the change in velocity, and the integral of velocity over time gives the change in position. Thus, the motion of an object can be described and predicted through the relationships among position, velocity, acceleration, and force. Newtonian mechanics is the model most aligned with human intuition, directly reflecting our basic understanding of the motion of objects and the forces acting on them in everyday life. Lagrangian mechanics is abstract. In its framework, the concept of force is absent, replaced by the Lagrangian function, the principle of least action, and the Euler-Lagrange equations. Lagrangian mechanics employs generalized coordinates, not limited to Cartesian coordinates. We will discuss these abstract concepts in Lagrangian mechanics in detail later. For now, it's enough to know that Lagrangian mechanics represents another mathematical model for describing the laws of motion of objects. Compared to Newtonian mechanics, it discards the concept of force as intuitively understood by humans, making it more abstract, elegant, and broadly applicable. In addition to Newtonian and Lagrangian mechanics, there are other mathematical models for describing and predicting the motion of objects. Among these, Hamiltonian mechanics is widely used. Hamiltonian mechanics is an extension of Lagrangian mechanics. It describes the evolution of systems using the Hamiltonian function, providing an equivalent but differently formulated mathematical framework to that of Lagrangian mechanics. In quantum mechanics, Hamiltonian mechanics is one of the fundamental mathematical tools. Regardless of the type of mechanics, all are mathematical models used to describe and predict the motion of objects, and they all describe the same physical reality consistently. Moving forward, we will focus on the fundamental framework of Lagrangian mechanics. Based on this framework, the derivation of relativistic dynamics will be simpler, and our understanding of concepts like energy and momentum in relativity will be deeper. Degrees of freedom refer to the number of variables that can vary independently in a system. To clarify, let's consider some examples to better understand the concept of degrees of freedom. A particle moving in space can be described by three coordinates, each of which can change independently. Therefore, the particle has 3 degrees of freedom. For two particles, each particle's position can be described by 3 coordinates, leading to 6 degrees of freedom in total. A pendulum swinging in a plane is restricted by the length of its string and the plane of swing. It has only one independent variable, typically the angle theta. Thus, the pendulum has 1 degree of freedom. For a double pendulum, each pendulum's swing angle is independent, so the system has 2 degrees of freedom. A system with n degrees of freedom is determined by n independent variables that define its position in space. Typically, we represent these variables with the letter q, accompanied by a subscript that indicates the variable's index. Q can be a Cartesian coordinate or unrelated to any coordinate system, like the swing angle of a pendulum. Each q is a value that changes over time. Q is known as a generalized coordinate in the Lagrangian mechanics model. The goal of this mathematical model is to find the laws of motion for the generalized coordinates. Next, let's delve into the concept of the state of a system. In classical mechanics, the state of a system at any given moment includes not only the values of the generalized coordinates q at that moment, but also the rates of change of these coordinates, known as the generalized velocities. We typically denote generalized velocities, which are the derivatives of q with respect to time, by q dot. For instance, the state of a particle moving in space at any given moment includes not only its position at that time, but also its velocity. The state of a pendulum at any given moment includes not only the angle of swing, but also the rate of change of this angle. The state of a system is determined by its generalized coordinates and generalized velocities. This fundamental understanding in classical mechanics aligns with our intuitive experience. Objects with different initial positions or velocities will follow different future trajectories. Thus, for a system with n degrees of freedom, its state has a dimensionality of 2n. A system with n degrees of freedom is n time-varying generalized coordinates. The values of generalized coordinates and velocities together determine the state of the system at any given moment. This is the backdrop for the model of Lagrangian mechanics. Lagrangian mechanics is based on the following principle. For a closed system with n degrees of freedom, there exists a real function L dependent on generalized coordinates and velocities, such that the motion of the system is governed by a partial differential equation involving L. This description is really abstract, so let's explain it sentence by sentence. We have explored the concept of degrees of freedom. A system with n degrees of freedom implies it possesses n generalized coordinates, and also means that the system's state at any given time t can be described by these coordinates and their respective velocities. There exists a real function L. Let's first examine the properties of function L, which includes generalized coordinates and velocities as its variables, specifically q and q dot, amounting to 2n variables in total. The value of L is a real number. Since the values of the generalized coordinates and velocities define the state of the system, L can be considered a function that maps the system's state to a real number. The function L is specifically known as the Lagrangian function and often simply referred to as the Lagrangian. The statement that there exists a real function L seems to state nothing specific, as countless real functions can be constructed from generalized coordinates and velocities. What then sets the Lagrangian apart? This is described in the third sentence. The system's equations of motion, or its evolution equations, satisfy a partial differential equation related to L. Specifically, the partial derivative of L with respect to generalized coordinates equals the time derivative of the partial derivative of L with respect to generalized velocities. It's important to note that this isn't just a single equation, but rather n equations collectively known as the Euler-Lagrange equations. Once the Lagrangian is defined, each equation in the Euler-Lagrange equations can be transformed into a second-order differential equation in terms of generalized coordinates with respect to time. Theoretically, the motion of n generalized coordinates can be well defined by these n equations. So, by determining the system's Lagrangian, we also define the Euler-Lagrange equations that describe the system's motion. The problem of solving for the system's motion is transformed into determining the system's Lagrangian. Another fundamental expression of Lagrangian mechanics is the principle of least action, which is mathematically equivalent to what we've just discussed. The action is the integral of the Lagrangian function between 2 points in time. Once the function qt is specified, the corresponding function q dot t is also determined, which together determine the value of the Lagrangian and thus the value of the action. Once the form of the Lagrangian is established, the action varies with qt functions, which is mathematically known as the action being a functional of qt. With values of q at time t1 and t2 fixed, different qt functions correspond to different values of action. The principle of least action states that the qt function that minimizes, or more accurately, stabilizes the action, represents the system's true trajectory. Previously, we mentioned that the Euler-Lagrange equations represent the system's evolution. In the context of the principle of least action, they become the equations that stabilize the action. How are these related? Mathematically, using variational calculus, it can be proven that the qt function that stabilizes the action satisfies the Euler-Lagrange equations. Thus, the principle of least action is equivalent to the fundamental principle of Lagrangian mechanics we've discussed. The foundational theorem of Lagrangian mechanics can be fully expressed as: for a closed system with n degrees of freedom, there exists a Lagrangian function, and the system's motion can be defined by the Euler-Lagrange equations, or equivalently, by the stabilization of the action. Compared to Newtonian mechanics, the fundamental principles of Lagrangian mechanics do not provide specific evolutionary equations for the system, but establish the existence of a Lagrangian function. How can we apply these principles to derive specific time evolution equations for a system? This will be our next topic of discussion. Let's explore the application of Lagrangian mechanics through some examples in classical mechanics and verify its consistency with Newtonian mechanics. In classical mechanics, the Lagrangian is defined as the kinetic energy minus the potential energy. The corresponding Euler-Lagrange equations describe the time evolution of the system. Consider a particle moving freely in three-dimensional space, with its position coordinates x, y, and z serving as generalized coordinates. The Lagrangian is defined as the kinetic energy minus the potential energy, where the kinetic energy is half the mass times the square of the velocity, and the potential energy is a function of the particle's position. The square of the velocity is the sum of the squares of the velocity components in each coordinate direction. This formulation expresses the Lagrangian as a function of the generalized coordinates and velocities. Write out the Euler-Lagrange equation for the generalized coordinate x, insert the corresponding Lagrangian function, and calculate the relevant partial derivatives and time derivatives. The partial derivative of the potential energy with respect to x represents the external force acting on the body in the x direction, and the second derivative of x with respect to time represents the acceleration of the body in the x direction. This is the dynamical equation in the x direction in Newtonian mechanics. Similarly, the Euler-Lagrange equations derived for coordinates y and z also yield the same results for motion along these axes, forming the set of motion equations in Newtonian mechanics. Next, let's consider a simple pendulum which has only one generalized coordinate, the pendulum angle. The speed of the pendulum bob is the product of the length of the pendulum and the angular velocity. The height of the bob is the negative product of the length of the pendulum and the cosine of the angle theta. Substitute into the Lagrangian to obtain a function dependent on the generalized coordinate theta and the generalized velocity theta dot. Write out the Euler-Lagrange equation, insert the Lagrangian, calculate the relevant partial and time derivatives, and simplify to derive the motion equation for the simple pendulum. In Newtonian mechanics, by analyzing the forces and accelerations along the tangent to the pendulum's path, we can derive the same motion equation. Moving on to the double pendulum, which has two generalized coordinates corresponding to the two pendulum angles. The Lagrangian is again the kinetic energy minus the potential energy. Despite the complexity of the system, the Lagrangian ultimately depends on the pendulum angles and their angular velocities, which serve as the generalized coordinates and velocities, respectively. There are two Euler-Lagrange equations corresponding to the two pendulum angles. Substituting the Lagrangian, we can derive the motion equations for the double pendulum. I won't demonstrate the specific calculations here, though they seem cumbersome. They actually only involve basic calculus knowledge. For the double pendulum system, Newtonian mechanics could also be used to obtain the motion equations, but the analysis would be highly complex. In this example, Lagrangian mechanics showcases its advantages. Through these examples, we've demonstrated the application process of Lagrangian mechanics, which involves identifying the system's generalized coordinates, formulating the Lagrangian, listing the Euler-Lagrange equations, solving them, and thereby determining the laws of motion of the system. Since in classical mechanics, our chosen Lagrangian is the kinetic energy minus the potential energy, the motion equations derived from the Euler-Lagrange equations are completely consistent with those of Newtonian mechanics. We have already explored the fundamental principles of Lagrangian mechanics, specifically the principle of least action and its applications in classical mechanics. Given the abstract nature of the principle of least action and its significance across all of physics, further discussion is warranted. First, let's consider the scope of the principle of least action. The principle of least action is not limited to classical mechanics. It is a universal principle applicable across all domains of physics. However, its specific mathematical expression can vary depending on the area of study. For example, in field theory, the action integral is not just over time but over space-time, involving multiple integrals. For instance, in quantum mechanics, the principle is expressed through Feynman's path integral formulation. Almost all physical theories can be described by a Lagrangian. Within the framework of Lagrangian mechanics, knowing the Lagrangian function allows one to describe the system's motion through the principle of least action and the Euler-Lagrange equations, effectively reducing all physical theories to a form expressible by the Lagrangian. From Maxwell's electrodynamics to Einstein's theory of gravitation to the standard model of particle physics, all can be described using a Lagrangian function. In classical mechanics, Newtonian mechanics can also be described equivalently through the Lagrangian, which is defined as the kinetic energy minus the potential energy. While the Lagrangian is not the only expression of physical theories, multiple equivalent mathematical models often exist to describe the same dynamical laws. For example, in classical mechanics, Newtonian mechanics is equivalent to Lagrangian mechanics. In quantum mechanics, Schrödinger's equation is equivalent to Feynman's path integral approach. In classical mechanics, the Lagrangian is kinetic energy minus potential energy. Mathematically, it can be shown that this Lagrangian is completely equivalent to the dynamical laws described by Newtonian mechanics, and we have already illustrated their consistency with some examples. However, in other domains of physics, the form of the Lagrangian does not necessarily equate to kinetic energy minus potential energy. Different dynamical laws correspond to different forms of the Lagrangian. What does kinetic energy minus potential energy signify? The action, which equals the integral of the Lagrangian over time, what does that represent? Unfortunately, the physical meanings of these calculations are not readily apparent. We can only understand them through mathematical language. However, in the context of special relativity, we will explore the origins of this Lagrangian function and its connection to Lorentz invariance. For those who like to delve deeper, a fundamental question arises. Why do the evolutionary laws of so many different types of physical systems all reduce to the principle of least action? While I cannot provide a rigorous answer, the universality of the principle of least action undoubtedly relates deeply to nature's symmetries, conservation of momentum and energy. Perhaps the deepest mysteries of the universe are embedded within this principle.